Okay, so last time we were talking about inverters, and we said that this same topology we can produce VDC on the load, minus VDC on the load, or zero, right? Depending on which switches we operate, and we drew the single pole double throw equivalent of this, meaning when I say single pole double throw, I'm referring to this configuration, right? This generalization of the two switches that represented as two nodes here with an arm oscillating between them. So we drew the equivalent circuit of that, and we derived the average voltage uh, between the reference and this node for on one side, and then the other side is the same. It's the same way to derive it, but if you may be operating with the complementary duty ratio, so if one arm may be operating with a duty ratio of D1, and the other arm may be operating with a ratio of 1 minus D1, or one arm may be operating with D1, the other arm may be operating with D2, right? Because the zero states, to get the zero states, meaning this is on top and this is on top, then they're not complementary anymore, right? So it's not D1 here and then 1 minus D1. It would be D1 and D2 in that case, right? And we derived both cases. And if D2 is equal to 1 minus D1, we saw the range of voltage being for the full bridge was minus VDC, where VDC was the voltage here, and VDC and minus VDC. That was the range for the full bridge inverter. How about for the half bridge inverter? The half bridge inverter, remember we had two capacitors here, and we had our single pole double throw representation of the switch here, and this was plus minus VDC, meaning the average value here, if this is operating at a duty ratio of D1, this would be average value equal to what? What's the average value of voltage at this node? VDC times D1, and then the average value of voltage at this node, this is a capacitive voltage divider, so it's taking the VDC and dividing it into VDC over 2 and VDC over 2. Hence, the average value of voltage here with respect to this reference, same reference, is VDC over 2, right? And then so the output voltage for the half bridge inverter was VDC times D minus VDC over 2. This was the average output voltage in this case. So if you take VDC by itself, it's 1 minus, so it's D minus half, right? And so D varies between 0 and 1, so if it's 0, it's minus VDC over 2, right? And if it's 1, it's VDC over 2, right? So the half bridge inverter can provide maximum voltages on the load of plus minus VDC over 2. The full bridge can provide a maximum range of voltage on the load plus minus VDC, right? So it depends on what the output voltage looks like and how you want to optimize the system, because again, you can produce the same output for the same output voltage that you want to produce on the load. You would for the half bridge configuration, you save on switches, right? You only have two switches in the half bridge and two capacitors. Versus in the full bridge, you have 4 different switches, right? So you save on the switches. But what happens is, for the half bridge, you would have to bump up the VDC to twice its value for the full bridge if you want to get the same output voltage on the load, right? To receive the same output voltage on the load, the half bridge converter would need a VDC of twice the full bridge inverter, right? And we saw that if you increase the DC voltage that the switches have to block, how does that affect losses? Remember our switching loss? Remember these triangles that we drew? What was the peak value of the triangle? The turn-on losses, turn-off losses. What was the peak value here for the power loss? Exactly, which V is the voltage that the switch is blocking, and which I, the I that the switch is conducting, right? So if we're blocking double the voltage, then it's going to affect switching losses, right? So it's an optimization process, right? So do you want to live with 4 switches for a full bridge inverter and use less voltage? Or do you want to live with a half bridge inverter and use 2 switches, but then increase the voltage at the input, which means you increase the switching losses. If you increase the switching losses, you may need a heatsink, right? So the cost that you save on 2 switches, you may have to invest in a heatsink, right? And if you want to make it small, definitely go for something without a heatsink. So maybe in that case, definitely go towards a full bridge, right? It depends on, again, depends on how you optimize, what the loads requirements are and how the system is optimized, what the ambient temperature is, etc., to be able to choose. Yeah. But I mean, these are 2 topologies that we can utilize to produce AC voltage here. And we said that with both topologies, actually with the square wave, and with both topologies, you can produce an output waveform that looks like this square wave, right? And with the square wave, we went ahead and said that, you know, if this is my voltage waveform, what would if this is applied across an RL load, what would my current waveform look like? Again, this is a fixed value, it's a DC voltage. If it's a pure inductance, the current will look like a ramp. It's not a pure inductance, there's a RL, there's a resistance as well, so it's an exponential waveform. The solution is natural response plus forced response, and it's an exponential. So the peak value of the ramp would have been here at the end of the positive voltage applied across the RL load. So the same thing will happen for the exponential current. Exponential current will look like this, will look like this, will look like this, etc., etc. Do these have the same harmonic content? No, they look quite different from each other. So then we said that we want to start working on how do we optimize the harmonic content, because at the end of the day, if the voltage and current waveforms have similar harmonic content, right, then you can transfer real power, right? If they don't have similar harmonic content, then you have currents and voltages at different frequencies that do not contribute to real power transfer, right? So that's the final objective here. So this is nice and simple. A nice and simple waveform. You are switching at your fundamental period. So if this is a 1/50 hertz, which is 20 milliseconds, this is your switching period. You are switching, this is your switching period T. Here you have device 1 and 1 and 3 on, and then here you have device 2 and 4 on, for example, right? For the full bridge, the 2 switches across each 1 and 3, and then 2 and 4. 1 and 3 and 2 and 4. You're making the switching every period, once every period. So the switching frequency is 50 hertz. So switching losses, we said, are proportional to switching frequency, right? It's the voltage times the base, the half base times the height of that triangle multiplied by the switching frequency. So here the switching frequency is so low, which is great. So you have very low switching losses. Right? So this is a nice approach. The idea of switching at fundamental frequency once every fundamental period is a nice thing. So there's a family of converters that was developed to make use of that. And then there was a family of converters developed to try to not make use of that and try to switch multiple times to increase the switching frequency. Right? So there are 2 main families of converters we will discuss, of inverters, that we will discuss. So again, just back to the current waveform. So we said that the current waveform for this voltage applied across an RL load would be the natural response and the forced response, right? The forced response would be basically the DC voltage divided by the resistance, right? And the natural response is the same as what we've been doing before, AE to the minus T over tau. Where would you get A from the initial conditions? What are the initial conditions for current? We just had the waveform for current up here. But my initial condition for current was, if this is my voltage waveform again, and this is my current. Again, it's a periodic current, so these are equal, and this would be I minimum, some I minimum, and this is some I maximum, and the current will always go to the same value of I maximum, right? So let's see what. So I know that at t equals 0, current is at I equal to I minimum, yeah, right? So the current waveform is equal to force response plus natural response. Now force response is the DC voltage or the source that you have divided by the resistance. Here you have a DC source and you have a resistance and inductance. In steady state, inductance is a short circuit and your source is DC, so it's VDC over R. That's your forced response. Natural response is AE to the minus T over tau. That's between 0 and T over 2, right? Between 0 and T over 2. You have one type of natural response for the circuit. And then at T of 0, we said the current will equal its minimum value. So at I of 0 is equal to I minimum. And then from here you can calculate the value for A and substitute it here. And then from T over 2 to capital period T, you have minus VDC over R as your forced response, right? And then BE to the minus T over tau, or with a shift of axis, equal to T over 2. And how would you find B? Same issue. B is equal to at T equals 0, or T equals T over 2 in this case, which is if you substitute with T equals T over 2 here, let me see, I want to zoom in. Right, if I substitute with T equals T over 2, that's my 0 condition, right? In that case, the current is equal to its maximum value at T over 2. Right? The current is equal to its maximum value at T over 2, so you will do that. You will, at T equals T over 2, current is equal to I max, and you were able to find B as well. Right? So you can find an equation for the current waveforms when it's rising and when it's falling. Right? You don't have a single equation for the current waveform anymore. Okay? So from an analysis perspective, what do you think we're going to head after that? If our objective is to look at harmonic content, we're probably not going to use a current equation that's very difficult to come up with a Fourier series for. We would probably go and use you can do that. You have the current waveform. You can try to find the Fourier series for this current waveform. Or, easier, is the voltage waveform. If you have the voltage waveform and you have your impedance, RL as an impedance, you can use your voltage harmonics divided by your impedance at each harmonic and find the current at each harmonic, right? Which is what we did something similar to before. So this is the equation for current from 0 to T over 2 and from T over 2 to T. That's fine. RMS value of current, they wrote that here. Again, they took one of these. They took because the areas are identical. The area on top the area here is identical to the area here. So they were able to, they just did it on half the cycle. So they took the current. So to find the RMS value of any waveform, you would take that waveform, right? Square it, find its average value, and put it under the root. So they took this equation for current here from 0 to T over 2, assuming it's identical, and it is identical because we're applying a square wave. A 50% duty cycle square wave is what we're applying, right? We're just 50%. So whatever's on top is whatever's equal to the bottom. So that's why they used half only the waveform and multiplied the average value here by 2. Okay? So you can find the RMS value this way. And then one thing I would like to note again is over here when we have VDC on the output, we have certain switches on, right? So if we go back to our circuit, our circuit looked like this. When this switch and this switch are on, I have this output voltage equal to, and this node is connected here, this node is connected here, right? So then the output voltage is equal to VDC, right? So when switch 1, I think they call this 3, are connected, the output voltage is VDC. And when switch 2 and 4 are connected, I think that's what they call them, we will have output of minus VDC, because we flip the terminals of the load. We just flip the load across the input. Yeah. So here we have 1 and 2 connected. Here we have 1 and 3 connected, and then here we have 2 and 4 connected. Fine. One thing to note is, let's see what the current waveform looks like. The output current waveform looks like this, right? We agreed that this is what the output current waveform will look like. Is this output current waveform unidirectional? No. Right? I mean, I had it on there. I shouldn't have. I should have waited. I should have asked before. But one thing to note is the current waveform at the output is not unidirectional, right? It ends here with a positive value and starts with a negative value. Did we study a switch that can conduct current in a bidirectional fashion, control current in a bidirectional fashion? No. Oh, switch meaning diode or MOSFET or BJT, right? None of these. All of these switches are able to control current only in one direction, right? So since this is the case, we know that not a single switch solution will satisfy the needs of what I want to do here. And we know that from from the chapter 1 slides. Remember that table that we used to go back to? Here we had, I think we had the same polarity for voltage, and then polarity for current was flipped. So we were using, since I have my representation for the single pole double throw configuration here, and I have current here that is bidirectional, right? This is my current. Current is bidirectional. And the voltage is unidirectional. This is my inverter, right? This is my full bridge or half bridge inverter representation. On the output on the load, the voltage is positive and negative, and it's an RL load, right? What does that mean? That means the current will also be positive and negative, right? It's a passive load. You give it a positive voltage to give you a positive current. You give it a negative voltage to give you a negative current. There may be a time delay, right? Depending on if it's an inductive load or a capacitive load, but it's a passive load, right? So since it's a passive load, it will respond in a similar fashion to what you provide. You give positive voltage, it will give positive current. But here I'm giving positive and negative voltage, so I'm expecting that the current will have positive and negative values, right? So current here in the inductor that we have in the equivalent representation of the inverter is bidirectional, and this is unidirectional. So I cannot live in one of these quadrants by itself. I have to live in this quadrant, these two quadrants together, right? Current is bidirectional, and voltage has a single polarity. So if you go back to the chapter 1 slides, you have to combine whatever was here and whatever was here together, right? So the combination, the resultant combination that will work is something that looks like this. Current can flow either this way or this way in this device, right? So you have to, I mean, in an inverter application, because, I mean, this is the same switch, right? Here I have switch, as long as I have positive VDC, that means I have this switch and this switch on, S1 and S2 on, right? These are the only switches that are going to be on when when the voltage is positive. But current, even though S1 and S2 are on, current is bidirectional, right? So since current is bidirectional and only these two switches are on, that means that these two switches should allow current to flow in two directions. So I cannot put a MOSFET by itself, or I cannot put a BJT by itself. I cannot do that, right? Because in that case, I will only have current flowing in one direction, right? But this is not true. This is, if you put the ideal switch representation, okay, remove the real switches and just put the ideal switch representation like we have here. When you put the ideal switch representation, you see the resultant current being both positive and negative. So since that is the case, current is both positive and negative, you have to select a device combination that accepts current to flow in both directions to substitute in the circuit in this instead of the ideal switch that we have, right? That is the. Or you could just go to the table, the 4 quadrants that we have in chapter 1 slides, and pick 2 of the quadrants and see how you can combine the switches in series or parallel. And we saw that we discussed this before. We saw with the parallel combination of the MOSFET and or the BJT and the diode is what makes sense in this case. Yeah. So that's something to note. And these diodes that are well, no, actually one thing I did not talk about here, I think. Can I have 2 of these switches on at the same time? Can I have S1 and S4 on at the same time? So I cannot have S1 and S4 because I will have a short circuit across the power supply, right? So, and the way I typically operate this is I operate S1 and S2, right? And then maybe S1 and S3 if I want to create some zero output. And then I turn on S4 and S3, right? So S1 and S4 are always complementary. And S3 and S2 are always complementary. But if I, complementary is a nice thing when you talk about digital circuits, right? But everything has a time to respond, right? By the time for you to turn off S1 and turn on S4, there's a time involved. So how close do you do that? Do you turn S4 before you turn off S1 so that you ensure that there's no gap at all? But in that case, there may be a time where you are having S1 and S4 on at the same time, right? Because again, you have S1 on. You want to turn it off and then turn S4 on, right? How fast do you turn S4 on? Do you turn S4 on and then turn off S1? Or do you turn off S1, give it some time, and then turn on S4? Yeah, you turn off S1, and then there's something called dead time that you insert. And here's what it's called: dead time or blanking time, right? This dead time or blanking time is time between the transition of S4 off and S1 off and S4 to be on, so that you don't cause a short circuit or a shoot-through fault is what it's called. Okay, so you always insert some dead time between them. Okay, so and if you look at our representation for the combination of 2 switches as a single pole double throw, this arm that oscillates between these 2 points, it's a good way to think of that, right? It takes time for this arm to move from one point to the other. This time is dead time, right? Why do you need it? Because you don't want to cause a short circuit across your supply. If you make it too big, then remember you're going to be losing parts of your duty cycle, right? You're losing parts of your switching period, right? So if you're losing parts of your switching period, then your ability to control duty cycle is limited, right? So it means that your limit on switching frequency has another consideration as well, this dead time effect that you want to include, right? So it's not the rise times and fall times of the switches only now. It's also the amount of dead time you need to insert, right? Okay, so we talked about the currents being bidirectional. So again, this is the output current, and then if I want to see what switch currents look like. This is switch current IS1 and IS2. And then this is switch current IS3 and IS4, right? Because here, S1, S1.
For that time, that means I'll have 0 in my voltage, and to be at maximum, then a 0 and then minimum.
For the dead time, let's see. No, you will have both switches off.
Yeah,
So this switch will be off, and this switch will be off, right? So S1. So sorry, let's draw it. So let's do it for the half bridge, for example. Actually, let's look at it this way. Yeah, when the device when the switch is up here, current is flowing in this direction. When the switch is down here, it's flowing in this direction, right? This is plus minus. This is plus minus VDC, right? So when you in the dead time, actually none of these switches are connected. None of these two switches are connected, but you will have current. Let me draw them actually with the diodes and switches is better, because then you can see that the current will have to flow through the diodes. When the switches are both off, the current will have to flow somewhere. So where is it going to flow? Let's draw the switches and diodes together. It will be easier to see. I think they called this 1 and then this 2. Sorry, my numbering was a bit off. Right? 1, 2, then top one is 3. Top one is 3, and then this is 4. And this is V output. When 1 and 2 are on, current is flowing, and then this is your DC source, VDC, right? When 1 and 2 are on, current flows from the DC source through the switch, through the load, back through the switch, to your source, right? Now we have to insert some dead time. Now I want to switch to what? 3 and 4, right? But I said I cannot switch to 3 and 4 right away. I have to turn off 1, right? And then turn on 4. And then same thing, I cannot turn on 3 right away. I have to turn off 2. And then turn on 3, right? Because that time applies in both cases. So let's see what happens. This is the current, this is the situation now, right? The blue is the situation now. And then we will put the black. So I now turn off 1 and 2, right? And I still didn't turn on 3 and 4. So what's going to happen during that time? Remember, this is an inductive load, right? This is a RL load. So current cannot be interrupted, right? Current cannot be interrupted instantaneously. So since that is the case, so what's going to happen? When I turn off 1 and 2 now, what's going to happen? So will current through the inductor change abruptly? No. So this is the same, right? 2 is off, right? 2 is off. I turned off 1 and 2. So where is current going to flow? It cannot go through 2 because it's off. Cannot go through this diode. Cannot go through 3. So it's going to go through this diode. And then it's also going to come through. Did I turn off on 4? I did not turn on 4, so it's going to come through right? And it makes sense. Current has flipped polarity in the supply. My supply current has flipped polarity. Right? So this is the freewheeling time. This is the time where you have, during the dead time, current is freewheeling through these diodes, through the freewheeling diodes. Right? So you will find that, yeah. So this is, let's say this is S1, and then this is D1. S3, D3. S4, D4. S2, D2. So current was flowing in S1 and S2, right? But initially it was flowing S1 and S2. Then what happened? Then it started flowing through, yeah, it started flowing through D4 and D3. And then I turn on what? Then what's, yeah, then I will turn on S3 and S4, right? So if I turn on S3 and S4, what happens? If I turn on S3 and S4, remember this now, the inductor current here is now being opposed by the DC supply. Initially it was supplied by the DC supply, right? Now there's voltage opposing current. So what was happening to the current, the blue current? It was decreasing in value. I mean, you have an inductor and you have voltage source opposing it, so the current is opposing it, so decreasing in value. And now the green, I mean, after you've exhausted that energy in the inductor, basically now you flipped the polarity of current by turning on S3 and S4. Yes?
Are we, for that short time, are we charging the source
Yeah, you're returning power is going back to the source.
from the inductor?
Yeah. Right, the current is changing polarity and voltage doesn't flip its polarity. Okay. And then, sorry, so S3 and S4, sorry. And then let's just finish the switches and then we'll do. And then what happens? Then I want to turn back turn off S4 and S3, but I cannot turn them off and turn S1 and S2 right away. So I turn off S4 and S3. What happens to the current? Yeah, so current will not change polarity. Current will continue this way. It will go through D1, right, and D2. Yes, ma'am. What do you mean the waveforms don't change? When S1 and S2 are on, no. And when S1 and S2 are on, what is the output voltage? S1 and S2? Huh? VDC. When S3 and S4 are on, minus VDC, yeah. So it's VDC minus VDC. VDC minus VDC. But when S1 and S2 are on here, during this time, I had a period of positive current, and then I also had a period of, so this is, so I had a period of positive current. Here, this is S1 and S2, S1 and S2 here. What was direction of current flow here? S1 and S2 current flows this way, right? D and then, so which one? So the black was positive and the blue was positive, right? But we said when S1 and S2 here in this period, remember current looked like this? Current looked like this, right? So this was period of positive current. Before it, there was a period of negative current. So and this is repeating. So it seems like, so this will repeat, right? So this is just a cycle you go through. So this was positive current through the inductor. This is also what? D4 and D3 is also positive current. How about this? Negative and then This is negative as well, right? So we had a period of negative current and followed by a period of positive, right? What am I doing? Yeah, then here, then this is positive as well, right? So it's negative and then positive, positive, negative, negative, right? So I have negative, positive, positive, negative, negative, positive, positive, negative, negative. So negative, negative, positive, positive. When we go around, I mean, this keeps repeating it, right? So this one here is this S1 and S2 being on, and then I turned off S1 and S2, but I still had positive current flowing, which is this section here, right? And that's D3 and D4 on. And then current goes negative, where S3 and S4 are on. And then there's another negative section here. D1 and D2 are on. Okay? Yes, ma'am.
Is that time a bad thing or a good thing?
That time? No, that time is not a nice thing to have. Because you lose duty cycle. You lose control. You don't have control. I mean, the current will flow. It's not, you're not controlling it yet. It's not up to you. You have to have it. I mean, can you, as soon as you turn off the switches, current will flow through the diodes. What if you didn't want that? What if you wanted to, if it flows through the diodes, you cannot interrupt it, for example. What if you want to interrupt it somehow?
Would you switch on to interrupt the light?
You will turn on S3 and S4 afterwards, right? You will turn on S3 and S4. So we turned on, after the current started flowing in the diodes, we turned on S3 and S4. But I cannot turn on S3 and S4 soon, I mean, so fast. I mean, there has to be a finite amount of dead time that I keep. Actually, it's not very relevant when we talk about switching at 50 Hertz. Because when we're switching at 50 Hertz, you are switching your switches at 50 Hertz, so it's not a big issue. Right? So I want to switch this switch every 50 Hertz only, and these switches every 50 Hertz only. I'm not worried about doing this faster than 50 Hertz. But when we talk about having multiple pulses per switching period, then it becomes a problem. It's not a problem here. That time is here. It's not a problem really. It's not. We don't care to control anything here. We're doing this at 50 Hertz. I want to switch only at 50 Hertz. So I would like current to flow in the diodes for this period of time. But if I have many multiples of these switchings happening in a single period, the number of these switchings that I can have in a single switch, in a single full period of the fundamental waveform is going to be limited by the amount of dead time that I have. Right? If you have to maintain a huge amount of dead time, then it eats away from your switching period. Right? So if you're eating away from your switching period, then you're going to limit the amount of switching frequency that you can raise the amount of switching frequency that you can have. So if you limit your switching frequency, then you have to live with two things: maybe larger inductors, larger capacitors, right? If you want to maintain the ripple within a certain value, right? Something else. Yeah, basically you will limit switching frequency, and you will have to live with larger reactive components. Yeah. Yeah.
Now that you mentioned when you have a larger inductor,
Yeah.
Just the current ripple will reduce, right? Or will something else change as well?
No, but here the inductor is actually your load, right? So here the inductor is actually your load, but in the case of multiple switchings per cycle, yes, it's the current ripple that will change for sure. But in the case of multiple switchings per cycle, we want to create a sine wave. Here, is this a sine wave? The output is the current a sine wave? It's not a sine wave. It's a highly distorted waveform that we really don't like, but it's an AC waveform. So if you have an AC motor that you plug across this voltage and this current waveform, it will run, no problem. But what we want to get to is something that looks like a sine wave, and we will be switching multiple times per period and creating something very close to a sine wave. Sure, in that case, if we want to maintain this ripple low, sure, that's the inductance is something that we can add to maintain lower ripple, yes, sure. I don't know if I answered your question. Yeah, in this case, I was just talking about the RL load. But if you want to control, here I'm not really controlling ripple because I'm not switching, I'm switching once per period. Right, so this is my ripple is my output current here. It's my peak-to-peak output current. I don't really have the notion of ripple in this case. But here, my peak-to-peak output current, for example, is this. This is my peak-to-peak output current value, but I have ripple here that I would like to maintain with a certain window, within a certain window. How do I achieve that? I cannot achieve that with fundamental frequency switching. Here, what we're doing is fundamental frequency switching. I'm only switching at 50 Hertz. This is 20 milliseconds. I'm switching one time. This is S1, S2 on. And then this is S3, S4 on. The diodes, I don't have to turn them on. They're already there. So here, what happened here was current was flowing through S1 and S2. What happened here, current was flowing through the corresponding diodes, and diode D1 and D2, or D3 and D3 and D4. Right? So here I had D3 and D4. Here I had S1 and S2. And here I had D1 and D2. And then here I had S3 and S4. Current was flowing through them. But I only switched S1 and S2 once at the beginning of this period, and then I turned them off here. Right? So this is my switch signal to S1 and S2. My switch signal to S3 and S4. Right? I only switched them once during this fundamental period. Right? So I'm not really controlling ripple as such. The output current is the output current. It looks like this. If you're going to talk about ripple, then this whole thing is ripple. Right? So the notion of ripple does not exist here. Okay, so we move to we covered this. We now have a justification for putting this diode and MOSFET, or diode and IGBT, right? Everybody's happy with why we put now a diode and a switch, not just a diode or not just a switch. And here they drew whatever we were talking about. So S1 and S2, and then before that with the corresponding diodes, D1, D2, and then D3 and D4, etc., etc. So these were the various the devices that were conducting current at the various times. And then we said, our objective is to finally get a nice waveform, nice voltage waveform that has as much of a sine wave-like fashion as possible, as well as the current waveform, right? So because that's our objective, of course, I have to do some analysis to look at where I stand now, so I can work on improving it, right? So the analysis will be based on Fourier series. We will not analyze the current waveform. We will not derive the Fourier series for the current waveform. We will go to our Fourier series for the voltage waveform. So for the voltage waveform, we have a square wave. Its Fourier series is V max over pi sine omega t plus sine 3 omega t over 3 plus sine 5 omega t over 5, etc., etc., right? So this is easy. We can analyze that. We take the different components of the voltage Fourier series, divide them by my impedance at every frequency, and find the current at every harmonic frequency, right? And from there, I can work on calculating RMS value. I can calculate THD. I can calculate crest factor. I can calculate whatever I want to calculate from the chapter 2 calculations that we did, right? And so that's what we will have to work on. So again, the peak value of the voltage is 4 VDC over pi. And if n is the fundamental, which for 1, third harmonic, fifth harmonic, etc., etc. And then the current will be the voltage divided by the impedance at that specific frequency. And then again, we said we can calculate the RMS current, calculate the power, we can calculate the THD, etc., etc. So they did this for us. They calculated the voltage harmonic, the impedance harmonic, the current harmonic, and the power, right? I mean, is everybody okay with how we do that? So the equations for that are here. The voltage harmonics are from the Fourier series. The current harmonics are from this equation, and this Zn is basically the square root of r squared plus n omega L squared, right? All under the square root. And then the equation for power is it's because here they have the real power will only be dissipated in the resistive load, so you can use V times I cosine phi, but it's very difficult because you don't have the you can calculate the angles of the impedance at every frequency, and then from this equation you can calculate the V n times I n cosine phi n. You can do that. Or since I'm looking at real power, I know that real power is only going to be dissipated in the resistor, so you can use I RMS squared times R as well, right? So that's another way to do that, to do it. And then, of course, you don't calculate everything until infinity. You will calculate something until a certain harmonic. I will tell you, for example, do it until the fifth harmonic, do it until the seventh harmonic, or whatever. Right? It's going to be close enough because at some point, again, the voltage harmonics become very low. The impedance at a higher frequency becomes high because n times omega L becomes a large value, right? So the current harmonic becomes negligible, right? So at some point, you're not adding much to your RMS value anyway. So how much is that? Depends on the shape of the waveform. So it can be up to the fifth harmonic, seventh harmonic, ninth harmonic, whatever. You will be told, for example, if you're asked to do that. Yeah. So here they do this for us, and they do the calculations for that square waveform up to the ninth harmonic. So there's the frequency, the voltage harmonics, the impedance at the various harmonics, the current, and obviously you see this is a lot smaller than the 9.27 fundamental, right? And then the power at the corresponding harmonic, right? So you see, but the amount of power dissipated fine at the third and fifth is not a lot, but it exists, right? I mean, there's power at the third and the fifth components that is, not very significant, but it is significant to some extent, yeah. So we would like to see a lot more of that on the fundamental. We would like to see a lot of that on the fundamental side because we would like to see a nice, beautiful sine wave and a nice, beautiful on the current and the voltage. If we do that, then all the components will be producing real power, and they will all be, because eventually we would like to create a voltage waveform that looks like a sine. If my voltage waveform looks like a sine and my current waveform does not look like a sine, I have a lot of power dissipation that's not contributing to real power. Here I have, I have something that is contributing to power at the third and fifth and seventh. It's a little bit smaller, and the ninth as well, yeah. So what happens if I improve my waveform? If I make my waveform closer to a sine wave? We talked last time about this waveform, right? We said that, if I add zeros here, I become a little closer to a sine wave, right? The other thing I should have said, okay, it's these third harmonics, for example. Here I have a simple RL load, but for a motor, for example, if you provide a motor with something besides the fundamental, you will not just get real power. In a resistive load, you will get real power. But a motor does not operate in that fashion. A motor, if you don't supply it with a three-phase balanced load, meaning only fundamental component, what happens is these third harmonics and fifth harmonics, they will cause heating because they are actually torques, but in the opposite direction. So the way we would, there's a mathematical theory called symmetrical components. We will study extensively in 459, symmetrical components. And symmetrical components theory says the following. If I have a three-phase balanced system applied to a three-phase load, I will have three-phase balanced currents flowing the load, right? If I have something that is not balanced, if I take, this is larger than, this is, let's say, A, this is B, and then this is C. This is larger than B and C, right? This is not balanced, even though they're 120 degrees apart, for example, but they're not balanced. So in this case, I cannot do this single-phase equivalent circuit business that I was doing, right? Do we agree or not? The single-phase equivalent circuit works fine if the three-phase voltages are balanced, because then the three-phase currents will be balanced, And then if I have a load, the currents will sum up here to 0, and no current will flow of my neutral, so I can connect the neutral of my source with the neutral of my load and extract this outside and do a single phase equivalent circuit, right? That's the whole story behind balanced systems, right? If the system is not balanced, if I'm supplying it with something like this, I cannot solve it. You cannot solve it using single phase equivalent circuits. You can keep it as a you can keep this circuit like this and do a loop here, and a loop here. You can do that because this is a circuit. Kirchhoff voltage law will apply, and you can try to solve it this way. But you will have a big set of equations that will all be interdependent on each other. And then it's simple with one source and one load. But can you imagine in a power system? In large power systems with tens of generators, tens of loads, it's not that simple to do something like that. So in a large power system, we need to find a way to simplify our calculations so that we can always go back to a single phase equivalent circuit or something that looks like it. And that's what symmetrical components theory does. Symmetrical components theory tells me that if I have a voltage source or a current source that is not balanced, I can chop it up. This is an unbalanced source. I can chop it up into two balanced three-phase sources, but one, okay, so if this is A, B, and C, right? One will look exactly the same. It will have the same sequence, right? If you're standing here, these are phases. They're rotating with time, right? They're actually changing with time. This is a frequency. They have frequency content there. If you're standing here, you will see A first, then B first, then C, right? And this is called the sequence of that voltage supply. So let's say we will call this positive sequence. So an observer will stand here, will see phase A, phase B, and phase C. Same thing, if you're measuring, you will see phase A first, then phase B, and phase C. That's positive sequence. So what symmetrical components theory tells me is that I can take this unbalanced system and I can chop it up into a positive sequence circuit, a positive sequence supply, meaning this is A, this is B, and this is C, rotating this way for an observer standing here. A, B, and C, right? And for an observer standing here, A, C, B. So for an observer standing here, I will now see something different. I will see phase A, then phase C, then phase B, right? It's like standing here and having this rotate the other direction, right? What would you see? You see A first, then C first, then B, right? So A first, then C, then B. So this will be negative sequence. What did Dr. Haytham say in the 338 course about flipping? Do you agree with, this is what the symmetrical components theory says, right? It says that I can take this, chop it into a source that looks like this, and then do what? Take this and apply it to my three-phase equivalent circuit. This is balanced, right? If I apply it to my three-phase equivalent circuit, what can I do? Solve it using a single-phase equivalent circuit. Nice and simple, right? Same thing, I can take this, apply it to the same circuit. Nice balanced three-phase, use single-phase equivalent circuit. And then it's another, you take this and chop it up to what's called positive sequence, negative sequence, and zero sequence. Zero sequence is, these will be the three-phase voltages, but they'll all be in phase, right? I don't want to talk about that too much now, but actually we can, because when you are supplying a motor, applying positive sequence balance, what happens? You produce torque, right? But what happens if you flip the terminals, Dr. Haytham was saying in 338? For those who took 338, it's not a requirement. If you flip the terminals, what happens to the motor in that case? Induction motor. Who took 338? Okay, what happens to the terminal, to the motor? Come on. You don't remember? So the motor will change speed. Will flip. The speed of rotation will flip. The direction of rotation will flip. It will be the opposite direction, right? So again, these three phases, what are they doing? They're creating a rotating field inside the machine. This rotating field, again, I'm not going to go through the theory of how to generate a rotating field, but this rotating field will rotate in a certain direction depending on the sequence of the supply. If you flip the sequence of the supply, the rotating field will rotate in the other direction, and you will rotate in the other direction. Okay? But now it's like taking what? It's now you're taking these, when you have an unbalanced supply, you're taking the field in one direction. And you're putting, at the same time, it's superposition, right? This is, I said, this is equivalent to these three together. But this can be 10 volts, this can be 1 volt, this can be 1 volt, for example. If it's an unbalanced system, they don't have to be the same magnitude, but this can be 10, 1, 1, 1. These are the balanced three-phase, but 1 volt, 1 volt, 1 volt. This is 10 volt, 10 volt, 10 volt, 1, 1, 1, right? This is positive sequence. So the motor will rotate in one direction, right? You're also applying, at the same time, a negative sequence, but with a lower value. So what are you trying to do? You're trying to rotate the machine in the opposite direction. If you apply voltage, you will have current, right? So you will have current in the winding, but what is it doing? You're actually decreasing the torque. This is actually opposing the torque produced by the positive sequence, right? So you're heating up the motor. So you're not going to get the same amount of torque. You brought the torque down, and what happened to the current? It went up, because you added some negative sequence current to your machine, right? So you had the positive sequence current contributing to torque. Then you put a supply in the opposite direction on the motor, trying to flip the direction, right? So what did that do? That supply, superposition, right? It's the source, and you have an RL load. I mean, same, superposition, current will flow, so you have to sum up the current. So that current will be additional current in the winding, and it's going to push torque, generate torque in the opposite direction of the positive sequence, meaning it will reduce torque on the output shaft. So you've reduced torque, and you have more current in the machine, right? So you're heating up the machine, basically. And then Dr. Aitham maybe talked about braking. No, he did. I'm sure he did. I'm sure he did. I'm sure he did. What did he say about methods of braking induction motors? No, he did. I'm sure he did. Huh? DC braking. DC braking, plugging or DC braking, right? So this is like DC braking. You're putting, DC is what? DC is a DC is a voltage in a, 1 voltage in space, right? One value of voltage in space. Is it rotating? No, it's not rotating. So same thing. This is not. It's a voltage that all 3 voltages are in phase. So if I have 3 voltages that are in phase with each other, I apply them to a 3-phase system. They're not balanced. I mean, they're not a balanced 3-phase 120 degrees apart anymore. So if they're all in phase, what happens? The currents that they will generate will also be in phase. Right? So if you apply them to a 3-phase system, right? These are 3-phase voltages. You will apply them to these 3 resistors. These are all in phase. They're not 120 degrees apart. So what will be the sum? 0? It will not be 0. It will be something, because these are all 3 in phase. These are 3 voltages that are in phase. They will cause current. So it will not be a balanced system either, right? These will be like plugging the motor, like applying a field in the motor that is stationary, right? Only 3-phase balanced systems, balanced phasors that are applied to a 3-phase load will generate a 3-phase rotating MMF. If you can do that, you can generate a rotating MMF with also 2 phases 90 degrees apart. That's single-phase machines operate in that fashion. If you put a voltage on one phase and a voltage 90 degrees apart, or if you've played with motors in a fridge, right, you will typically have a capacitor there, called a capacitor, a starting capacitor. Single phase, you talked about single phase motors in the class, right? 338, you talked about single phase motors, right? And you remember Dr. Haytham putting a capacitor in there to the starting capacitor, right? What was that capacitor doing? Why was it starting? Yeah, it was creating this phase shift, because you only had a single supply, right? You had a single supply, but this capacitor is phase shifting by 90 degrees, taking the voltage, phase shifting by 90 degrees, and applying it to a second phase. When you do that, you have 2 phase voltages that are 90 degrees apart. When they rotate, they generate a rotating MMF. But now I have these are 3 in-phase voltage supplies that are not going to create a rotating MMF. but they're going to create current in the motor. This current will create torque. That torque is not going to rotate. It's stationary torque, right? So this can plug the motor, can break the motor. This can rotate in the opposite direction, and this will rotate in the direction you want it to rotate. So if you have too much of the negative sequence or too much of the zero sequence, it's a problem. Okay? Why are we talking about all this? Yeah, because the third harmonic, again, that's in 459. We'll talk more about that. But in the third harmonic is a negative sequence as seen by a motor, right? When it will be it's a negative. Sorry, the third harmonic is a zero sequence. Fifth harmonic is a negative sequence. So if you have a negative sequence, power in the negative sequence, power in the zero sequence, then what are you doing? You're going to be breaking your motor, heating your motor, not contributing to torque production. That's why I was trying to explain that, right? So in an RL load, that's not very clear. Okay, fine, I'm generating real power. What's your problem, right? But if I'm applying this to a machine, then it's a problem. So that's why I would like to improve it. And the biggest chunk of industrial loads are motors, right? So you can that's the justification. Justification is, okay, you cannot live with low-order harmonics that are producing power, because then you're going to be heating up motors unnecessarily without producing the torque that you require. So you're going to have to derate all your equipment, which doesn't make sense. You derate transformers, derate motors, etc., etc. So how do you solve that? You try to improve the harmonic content of your waveform. How do you improve the harmonic content of your waveform? You cannot do it with a pure, 50% duty cycle, fundamental frequency switching, just a pure square wave at 50 hertz. You cannot do that, right? So how do you improve it? That's the objective of the rest of the things that we're going to discuss. One way to improve it is to add some zeros here. That's one way to improve it, okay? So why is that one way to improve it? Again, if you look at, okay, so if you add some zeros here, remember we said that to obtain zeros, we operate what? The two top switches or the two bottom switches together, right? So here they show you which switches are on. So S1 and S2 are on during this period. And then during this period where the zeros are, you have S2 and S4, which are the bottom two switches. Or S1 and S3, which are the top two switches. So you're creating zeros here and here. Okay, so zeros here are the top two switches. And the zero here is the bottom two switches. S2 and S4. Okay? So, again, to see how this adding zeros helps, you have to go to Fourier series again. Right? So, they did the Fourier series for us here. And the nth harmonic of voltage is what they've calculated for us, is equal to 4 VDC over n pi cosine n alpha. Right? So, what does this tell us? It tells us that, like for the fundamental, for example, I have 4 VDC over pi cosine alpha. That means I can, if I choose, or for the nth harmonic, for example, I can, if I want to eliminate the third harmonic, right? What do I do? So V3, I want V3 to equal 0. So V3 equals 0. Can I make this V3 equals 0 using this value of nth harmonic voltage? If I make my cosine n alpha equals 0, then I can make V3 equals 0, right? So if I make alpha equal to 90 over 3, right? 90 over 3 is 30 degrees, right? So if I make alpha equal 3 times 30, which is 90, right? So for the third harmonic, I choose alpha equals 30 degrees. So 3 times 30 is 90 degrees. So what's cosine 90? 0. So I was able to eliminate the third harmonic completely, right? But what was the consequence? Did I affect my fundamental or not? Because at the end of the day, what am I trying to do, guys? We're trying to maximize the fundamental for the same DC voltage, right? I want to have a certain DC voltage and then maximize the fundamental that I can generate and minimize all the other harmonics. That's the objective of this, everything we're trying to do with inverters, right? So I chose alpha to be 30 degrees. If I choose alpha to be 30 degrees, I eliminated completely V3. But as a consequence, what is cosine 30? Something 0.86 blah blah blah, right? So I also affected my fundamental, right? Because cosine alpha is also affecting my fundamental, right? So that's something that I have to live with this type of switching waveform, right? So I was able to eliminate third, but did I eliminate fifth? No, because 5 times 3 is 150. What's cosine 150? Some value, right? So it's a negative something, right? So I have a voltage, a negative voltage of some value here, right? So I was not able to eliminate the fifth harmonic, right? So with one switching per cycle. So before I had what? Before I had fundamental frequency switching. So every switching period I switched one time only, right? Now when I did this, adding these zeros here, what did I do? So I have one pulse per cycle, right, with some zeros in the middle. I was able to eliminate one harmonic, and I can choose which harmonic it is, right? I can choose alpha to be whatever I want. I can eliminate the fifth, right? I can eliminate the ninth. I can eliminate whatever I want. But typically, you want to eliminate the lowest order one, so you eliminate the third. The lower the order of the harmonic, the bigger the effect it will have, right? Because again, the impedance, the current will be the voltage divided by the impedance. Impedance will be small. Voltage divided by the impedance, which is the current, will be a larger value at that. So you want to eliminate the lower order harmonics. So this is one way to control and improve the waveform, and eliminate one harmonic. Can I do better? Let's see what people did. So we agreed that if alpha is 30 degrees, I can eliminate one harmonic, right? So let's see how we can do this graphically. Let's the graphical representation of what we're trying to do. Fourier series is a technique to take your waveform and chop it up into a set of sines and cosines and average values, right? So how would you calculate your sets of sines and cosines and average value using these three equations, right? That's from Fourier series. Your average value is this. An in this equation is the integration of the waveform multiplied by cosine n omega t, and then this is the bn values. Okay, so we're dealing with AC waveforms, right? So these AC waveforms don't have an average value, and if we are choosing a reference properly, then we can odd symmetry, even symmetry, all that business, and we can get rid of the ANs as well. Right? We can get rid of one of the Fourier series. We can write it in terms. We can write any waveform in terms of a set of cosines or sines if I have the pleasure of choosing where my reference is. Right? So let's say we get rid of our ANs and average value because that's AC waveforms, and only left with this integration or this value for this integration for the Fourier series. Right? Integration is graphically nothing but the area under a curve. Right? So this is the area, this is my function f of t multiplied by sine n omega t, right? So what is my function? My function is a single pulse per cycle, right? For now, if my pulse is a single pulse if my f of t is a single pulse per cycle, my pulse multiplied by the sine is going to be 0 here and 0 here, and to be equal to the sine. Assuming this is 1, this pulse has a maximum value of 1, right? Then your output will be equal to the sine wave during this period, right? So if you integrate over this period here, again it's 2 times the full period. So I did it only over half of the fundamental period, right? So if you do that, and n is 3. N is 3, it means I have 3 of these sine pulses, 3 of these humps of the sine wave, while I have 1 of the pulse, right? So for a full period, I would have a positive pulse and a negative pulse. For a full period, I would have 3 fundamental cycles of the sine wave, right? I have a third harmonic for for this sine n omega t. And I have multiplying that by my f of t, which is my single pulse per cycle waveform. If I do that, the area under this curve plus the area under this curve plus the area under this curve is 0. Because I chose alpha to be 30 degrees. I don't know if it's clear. Okay. I'm not sure if it's clear. Okay. I'm taking my f of t. I would like to resemble this integration graphically to see if I can improve on this idea of, I had, with one pulse per cycle, I added some zeros. And with proper choice of my width of how long I add zeros, I was able to eliminate one harmonic. Right? That was what we did. So we want to represent that graphically. So I take my one pulse per cycle, which is this waveform here. I know from my analysis of my one pulse per cycle waveform that if I choose alpha to be 30 degrees, then I will eliminate the third harmonic. I know that from here, from this analysis. So if I choose alpha to be 30 degrees, I will draw a third harmonic sine wave, and I will draw my single pulse per cycle waveform, right? I drew them on top of each other here, right? If I multiply them by each other, assuming this here has a peak value of 1, right? If I multiply these by each other, then the multiplication here will be 0. The multiplication here will be 0. And the multiplication within this period will be the sine wave. Same shape as the sine wave. It's scaled up or scaled down. Doesn't matter. Depending on the value of this. If it's 1, then it's equal to the sine wave. Right? So this is the area under the curve of the two waveforms multiplied by each other. This area under the curve is the multiplication that I have here. Right? If this multiplication is 0, then this integration will also be 0. Right? So if I chose alpha to be 30 degrees, this area and this area and this area will sum to 0. Right? So if they sum to 0, that means the integral here, Bn, will also be 0, which means I've eliminated the third harmonic in this case, because I've put 3 of these humps of the sine wave, or I put 3 sine wave full cycles in my full period, or 6 of these humps in the full period, meaning 3 of the full cycles in the full period. Does everybody get this? Okay. So now with this in mind, if I want to eliminate the fifth harmonic and I have a single pulse per cycle, what do? I would draw, instead of draw 3 of these, I would draw 5. Right? I would draw 5 of these, and I would find the angle that would also give me the sum of all these areas to be equal to 0. Right? Same thing, same method. And here I still have the single pulse per cycle. And if I go back to here, how do I eliminate the fifth harmonic? I want to eliminate the fifth harmonic. Then it's 90 divided by 5, which is 18. Right? So that's how they drew this. By choosing alpha is equal to 18, they were able to eliminate the fifth harmonic. I cannot eliminate both at the same time. I cannot do that with a single pulse per cycle. But what people realized is, okay, I can make use of what's going on here graphically, and maybe I can add more than one pulse per cycle. If I add more than one pulse per cycle, and I do the same trick that I just did, right? I have 3 pulses per cycle. And I draw a third harmonic and a fifth harmonic, right? And if I now have these areas under the third harmonic and these areas under the fifth harmonic curve to sum to 0, then I've been able to eliminate the third and fifth harmonic using multiple pulses per cycle. Is everybody following or not? No? Are you following this? You following this? Okay, so if you're following this, then the...
I can cancel all the other frequencies, I just keep the fundamental.
No, you will always have a fundamental. You will always have your fundamental. Your fundamental will always be there.
Yes, I can just cancel 3, 5, 7.
But with a single pulse per cycle, let's put the fifth harmonic. Take this fifth harmonic waveform, and put it on top here, but keep alpha equals 30 degrees. If you keep alpha equals 30 degrees and you put your fifth harmonic here, and you sum the areas, they will never be zero.
That's not ideal. Like if I keep doing for the third figures, when I keep pulsing,
Yes?
it means I can cancel all my other
Sure, I agree. Not all of them, maybe not 100% of all of them, but you will be able to cancel a lot of them. Sure, I agree with you. But again, if the more harmonics you want to cancel, the more of these pulses you want to put, right? You agree? So if the more of these harmonics, the more of these pulses you want to put. But at some point, you're going to be limited by the amount of switching, by your switching frequency and by your switching period, and your dead time, right? So I agree with you 100%. Yes. So I'm glad. I mean, it's good. I mean, I agree that if you keep adding more pulses, you will have more flexibility. If you add this more flexibility, then you go back to the Fourier series every time, and you will do the analysis. And yes, you can calculate more, cancel more harmonics, but there's a limit, right? So people have been working on modulation schemes. That's where a big area of research is on modulation schemes. On modulation schemes to reduce switching loss, modulation schemes to reduce harmonic content, modulation schemes to reduce, I don't know, to improve power factor. I mean, they come up with modulation schemes to decrease peak values of current. I mean, people just keep working to better utilize your DC value. Because remember, what we saw here was what? We saw that in here, we were also, the fundamental period, the fundamental component, the value of the fundamental component was being affected by the angle that I was choosing, right? So it was actually decreasing, right? So if I chose alpha equals 30, I canceled the third harmonic, but I decreased my fundamental component, right? Is that good or bad? It's not a good thing. But it's not a bad thing either. All you need to do in this case to get a certain output is to raise the DC voltage at the input, right? Because here you have control over that. You can raise the DC voltage at the input. So maybe if you have a transformer feeding it, increase the turns ratio, or if you have a power supply feeding it, you have to raise the DC value of the power supply. If you can live with that, you can live with it. But what if you can't? Then people are working on modulation schemes to do that. They are working on modulation schemes to be able to reduce harmonic content, like we did here, as well as maintain a large fundamental value. People working on modulation schemes and converter topologies that allow you to do that. So we'll stop here. So I think the message is now clear what we want to do next. What we want to do next is look at modulation schemes and converters that will help us bring the waveform closer to a sine, so eliminating harmonic content, and as well as trying to not affect the fundamental component RMS value, for example. Right. So we'll stop here, and next time we'll address that. We discussed the half bridge, so I'm not just going to discuss the half bridge again. But we're going to discuss now converter topologies different converter topologies, for example, that can bring us closer to a sine wave. So initially we had some zeros only, but what if we add some values in the middle? Maybe it will be helpful, right? So what if we add some values in the middle and also have multiple pulses within that, right? So we had initially a single pulse, right? Single pulse with some zeros. Then multiple pulses. So, single value, 0, single value, 0, single value, 0. It gave us something. But now there are other converter topologies, multi-level inverters, for example, that can give us multiple values, multiple levels. How about if I have these multiple levels and add as well, okay, this value and 0, this value and 0, this value and 0, this top value and 0. Then I have even better control, right? So we're going to head to there, right? So that's the converter topology that will improve the shape of the waveform, and then we will add pulses within those, right? To add some more pulses within those to see how I can improve the harmonic content even further. That will be the objective of our next class. We will not be able to finish the whole chapter, but I hope you get the picture, at least the objective. Yeah.